The third speaker for today will be Denis Auroux from Snowy Harvard, and the talk is Mirror of Curves and the Fukaya categories. Please.
Okay, well, thank you very much, and I'm glad to be here to, at least virtually, to help celebrate Sasha Efimov's EMS Prize. It's not clear that I do any meaningful non-commutative geometry, but on the other hand, Sasha and I have collaborated on the more symplectic related side of his life, and I've known him since he was incredibly young, and he's still incredibly young, but it's still been a lot of years since. I don't know how he manages to stay young forever, but anyway, so I want to talk a bit about mirror symmetry for curves, and I want to start with a part that's maybe more established, which is about how to think of constructing mirrors to curves viewed as hypersurfaces inside some ambient space. And then I want to move on to joint work in progress with Sasha Efimov and Ludmil Kedzarkov about Floer theory and Fukaya categories for trivalent configurations of Riemann surfaces. So, all right. So let's start with the beginning of the story. So if I have a hypersurface inside, say, the algebraic torus Gm to the n, or a toric variety, and the field of definition I have in mind is typically going to be something like a Novikov field. But you could think of this as a degenerating family of complex hypersurfaces. I mean, this is not the crowd to worry about this, I think, but just in case. Anyway, so out of the data of a defining equation, say some Laurent polynomial, then one can produce a candidate mirror-Landau-Ginzburg model, which consists of a non-compact toric variety of dimension 1 more than the ambient space, so 2 more than h, equipped with a superpotential. And then homological mirror symmetry predicts two things. On one hand, a relation between the Fukaya category of the hypersurface H and the derived category of singularities of the Landau-Ginzburg model. So this is something that has been studied a lot in the literature. Just thinking about curves, well, the first instance, I would say, of this for curves of general type is Seidel's paper on the genus 2 curve, followed immediately by Sasha Efimov extending this for all closed curves of genus at least 2. Then with Abu Zaid, Efimov, Kedzarkov, and Orlov, we studied the case of the pair of pants or other punctured spheres and their covers. Heatherly extended this to all open Riemann surfaces, and more recent work using microlocal sheaves or not using it extended this to further generality. But the other part of mirror symmetry is what I want to focus on today. So this is the expected equivalence between coherent sheaves on the hypersurface H and some Fukaya category of a mirror Landau-Ginzburg model. So this is something that's part of a long-running joint project with Mohammed Abu Zaid, which someday we will actually maybe bother to write instead of giving talks about it. My student Catherine Canizzo also wrote a very nice thesis about the case of a genus 2 curve seen as embedded inside its Jacobian. So the issue with this construction is that the mirror that we get depends very much on the choice of ambient space. It depends very much on the choice of an embedding of H into some ambient space V, even though it seems that the geometry of the critical locus of the superpotential doesn't, at least at a large scale. If you look in the details, there are some quantum corrections that are kind of a bit pesky, and it's not quite clear what's happening. And of course, when I say it doesn't depend on the choice of ambient space, sure, but you still need to think either of H as a non-Archimedean analytic space or as a degenerating family of complex spaces. So, all right. So, in the hopes to actually get to my work with Sasha and Ludmil that I want to talk about, I'll be brief about this part. But the construction of mirror that I alluded to in the previous slide starts from the defining equation of a hypersurface in the algebraic torus or in a toric variety, and produces a mirror basically out of the tropicalization of the defining equation. So the tropicalization of the Laurent polynomial used to define H. So if you want what it does at the level of valuations, since we're over in the Novikov field, defines a piecewise linear function on R to the n, and what sits above the graph of this function can be viewed as the moment polytope for a toric Kähler variety. And then there's a way to equip this with a regular function, and that will be the candidate mirror. So rather than do the details of the construction, I want to just give some examples. So the most basic and most important example for all subsequent applications is the pair of pants. So you can get the pair of pants as just a linear subspace of the two-dimensional torus defined by the equation 1 plus x1 plus x2 equals 0. So if you tropicalize this polynomial, you'll get max of 0 and the two coordinates. And what sits above the graph of that looks like it's congruent under GL3Z to an octant in free space. So the mirror ends up being C cubed with the superpotential given by the product of the coordinates. So what will be important to us soon is that the critical locus of this superpotential is the union of the coordinate axes in C cubed. Another example to move up the hierarchy of surfaces, skipping a few along the way, if I look at a closed elliptic curve viewed as a divisor in some toric variety, I can do this by starting from the punctured elliptic curves x plus y plus 1 over xy plus t inverse equals 0. And whose tropicalization looks like this, and then compactify in a suitable toric variety. Then the mirror ends up being the total space of a canonical bundle of P2 with a superpotential given by whatever it is, but the notable feature is so Y is a non-compact threefold, and this function on it is Morse-bot along a smooth cubic elliptic curve inside the base P2. So the critical locus of this Landau-Ginzburg model is smooth, and it's in fact the usual mirror elliptic curve to the elliptic curve we started with. Now things get more exciting when we go to higher genus, and this is where we really need this machinery. So the mirror of a curve of genus at least 2 embedded in a toric surface ends up being now a threefold together with a superpotential whose critical locus ends up being a trivalent configuration of CP1s meeting in some triple points. And just by counting, there's 3G minus 3 CP1s in the critical locus and 2G minus 2 triple points. So near each of these nodes, there's a local chart where this looks a lot like C cubed with a product of the coordinates. But these get assembled together in a certain way as dictated, in fact. Each of these charts is mirrored to a pair of pants, and the tropical limit, or if you want non-Archimedean geometry, determines for us a pair of pants decomposition of our genus G curve. And this pair of pants decomposition tells us how to assemble mirrors of pairs of pants together. So one way to think of this is, it's kind of hard to picture. But there's these like modern art sculptures by Jeff Koons made from balloons, and don't look too closely because it's not trivalent, but it's very much the kind of picture that we hope to have. So he's been making mirrors of curves without knowing it. All right, so one way to study mirror symmetry for these things is to look at the Fukaya-sidal category of these Landau-Ginzburg models, Y, superpotential. And you can go about it. It's kind of slightly painful, as usual with Fukaya categories, and not much fun. So here I'm mostly putting this on the slides to convince you that it can be done, and it's not particularly pleasant. So the way that you can construct a fiber-wise wrapped Fukaya category for such a Landau-Ginzburg model, first of all, I should say, because these mirrors are non-exact, you should be able to use technology related to sectors and so on to understand what's going on, but that technology is not available in the non-exact case yet. There are some obstacles. So far one has to use actual symplectic geometry. So the way we do this is we look at Lagrangian submanifolds of Y, which are admissible with respect to this superpotential. And also we assume they don't bound any holomorphic disk. That kind of simplifies the definition of Floer theory a lot. So the admissibility condition basically says, Y is a toric variety. And so the superpotential is a sum of toric monomials. And basically what we want to assume is that each of these toric monomials has a locally constant argument at infinity wherever it becomes large. So there's like this admissibility condition that says that the argument of each of the terms that show up in the superpotential has to go to a constant at infinity. So technically, this allows us to obtain control over holomorphic disks, but most importantly, this also imposes a stopping condition. Basically, this stops the wrapping of Floer homology in the directions where the argument of these various monomials in the superpotential would cross some forbidden value. And then one defines morphisms in this Fukaya category by a limit process where we perturb Lagrangians by a Hamiltonian flow that pushes everything in the positive direction. So increases the argument of all toric monomials at infinity, but depending on whether these monomials appear or not in the superpotential, you either increase them in a bounded interval without crossing the stop, or you increase them all the way to infinity, namely you wrap. So there's a construction of fiber-wise wrapped Floer homology in this setup, and you can get to a proof of homological mirror symmetry, in fact, in a lot of generality, basically for all complete intersections in toric varieties. But so the example I want to use today is that of just the mirror of a pair of pants, because this will serve as motivation for what comes next. All right, so let's look at the mirror of a pair of pants that's C cubed with a potential given by the product of the coordinates. There's a minus sign, but it's not very important. So the Lagrangian submanifold that I'm most interested in is something that's obtained as follows. So keep in mind, okay, so what's the geometry of this Landau-Ginzburg model? The central fiber, product of coordinates equals 0, is the union of the coordinate hyperplanes in C cubed, 3 copies of C squared. We're actually not going to look here at all for now. That's what comes later. Instead, the other fibers, if I set this equal to a non-zero constant, look like C star squared. In particular, the fiber above a point in the real negative axis has a preferred real positive part, r plus squared inside C star squared, where the coordinates Z1, Z2, Z3 are positive, and their product takes a fixed value. And now you can transport this Lagrangian in the fiber along a U-shaped arc in the base of this fibration given by W0. So this produces new Lagrangians inside all of the fibers over the U-shaped arc, which are the images of this little L0 under the monodromy. And if we start taking on the perturbation used to define morphisms in the Wrap-Fukaya category, we also need, well, so we need to push this U-shaped arc in the base slightly counterclockwise. And within the fiber, we need to wrap the arguments of the coordinates zi a lot at infinity. So if we want to compute now the Floer homology of L0 with itself, well, we have to look for intersections between L0 and the perturbed copy of L0. So these happen in two different fibers, over here at -1 and over here somewhere on the other side. At -1 inside the fiber, what we see is the wrapped Floer homology of little L0 with itself inside C star squared. And if you want, this is a calculation that's mirror to the endomorphisms of the structure sheaf on the algebraic torus K star squared. So this is going to produce for you Laurent polynomials in two variables. In the other fiber, we see in fact a very similar picture because the monodromy bends a little bit my Lagrangians, but the wrapping eventually will still produce Laurent polynomials in two variables. However, those generators live in degree -1. Also, I think I'm being told that this is not the right grading to whatever. Anyway, this lives in degree -1. And then there's a connecting map in the Floer differential which counts holomorphic curves which live over this region in the base. And the calculation shows that this is just multiplication by the variables 1 plus x1, I mean by 1 plus x1 plus x2 viewed, as an element of a Laurent polynomial ring. And so in fact, the self-Floer cohomology of big L0 ends up being isomorphic as a ring to the quotient of Laurent polynomials by the ideal generated by 1 plus x1 plus x2. And this is indeed regular functions on the pair of pants. So you can do similar calculations for other hypersurfaces or in much more generality, but I think I am not going to get into that, even though there's a lot of very nice geometry. Instead, so I want to point out that the calculation works. You can prove it. Writing up the details has been more effort than Mohammed and I have been able to put into it. At this point, probably, if we were to die suddenly, I think one can reconstruct from the various sets of Miami talks that I've given about it, if you can, if you really care. Catherine Canizzo's thesis also about the case of genus 2 curves inside abelian varieties gives a template for how you do this. But there's a fundamental problem with this approach if you believe that there should be mirror symmetry for higher genus curves in their own right, rather than as a hypersurface in some ambient space. And I mean, you see this already on the example that we had. See, all the calculation was really done inside C star squared, which was the mirror to the ambient space in which the pair of pants is embedded. And we just produced the correct answer out of a mapping cone, which basically amounts to calculating the ring of functions on the pair of pants by resolving the structure sheaf of a pair of pants in terms of sheaves on the ambient space. In this case, just the trivial structure sheaf and the mapping cone of the defining equation of the pair of pants. So the whole calculation works at the level of the ambient space. And instead, we'd like to forget the ambient space and focus on the curve itself. So there's some encouraging examples if you look at small genus. For example, if you remember that for a smooth elliptic curve, the mirror ends up being Morse bot along a smooth cubic elliptic curve, which is the usual mirror. So you'd like to say, well, okay, maybe we want to just look at the critical locus of this Landau-Ginzburg model. So you might ask, how does mirror symmetry for the critical locus C relate to the case of this Landau-Ginzburg model Y, W? And the answer in the case of Morse-bot superpotentials is the notion of thimbles in Lagrangian Floer theory. So the idea is, if I have a Morse-bot vibration, then I can look at its critical locus. I can take a Lagrangian inside the critical locus. So in this case, I'm calling it again little l. Sorry, I don't have very many different letters. Maybe I should use the Cyrillic alphabet in a few places, but too late to change that. Anyway, so I have a little l, which is just going to be an S1 inside the critical locus. And by parallel transport, so by looking at the space of all points in Y, W, which live over, say, the real positive axis, and for which the gradient flow of the real part of W converges to little l, I obtain what's called the thimble associated to L, which is a Lagrangian S1 times R2 inside the total space. And an elementary argument shows that this defines actually a functor from the Fukaya category of C to the Fukaya category of Y, W. There's a slight lie in what I'm saying, but close enough. And so this is basically, what you would like to do in general. So the problem, of course, is that a lot of our superpotentials do not have a smooth critical locus. So there's a few basic cases where, so if, for example, if you take a cylinder, then the mirror is just going to be another cylinder. That works fine. For the pair of pans, there's actually a funny construction where you take the critical locus, which we said was the union of the three coordinate axes in C cubed, with XYZ, but you realize that in fact there's a Knurrer periodicity type result at work that relates this to the curve xy equals 0 inside C squared. So my student Maxim Jeffs is basically checking statements about the analog of Knurrer periodicity for symplectic geometry of Landau-Ginzburg models. And this shows that, yes, you can define a Fukaya category of a nodal Riemann surface as basically a quotient of a Fukaya category of its smoothing, and that will produce valid versions of mirror symmetry. But you can't do things like that in genus 2 or higher. I mean, there are some mirror stacky curves. There are some stacky nodal curves that serve as mirrors that have been studied by Troyman, Gamage, and Shende, Lekeli, and Polishchuk. But at this point, I don't know how one would associate a Fukaya category to one of these. So instead, what we want to do is look at the geometry of trivalent critical loci. So, all right. So remember, we're looking at the mirror of a genus 2 curve. And if we think of it, say, as sitting in a toric surface, then we get mirrors that are trivalent configurations of CP1s meeting in triple points. And so the question would be, how do we associate a Fukaya category directly to such a trivalent configuration of Riemann surfaces? And it should be emphasized that we are not necessarily trying to say, consider this union of Riemann surfaces as a space in its own right without any extra data. Maybe the better analogy is when one starts to think about the derived category of singularities of a Landau-Ginzburg model, there's a result that says that you can reduce to a formal neighborhood of a critical locus, and that now becomes this trivalent configuration of curves, but together with some extra data, something that's been called sometimes a perverse curve, that kind of keeps track of what exactly is happening at these trivalent points. So similarly here, we are not really saying we can associate this to just the configuration of P1s, but I mean, there's some extra data hiding possibly in the triple points. Okay, so the naive construction that we would like to do imitates what happened for the elliptic curve, where you take Lagrangians in the critical locus and you try to produce thimbles out of them. And so the question here would be now whether we can produce, sorry, so one thing I should say first is it's kind of understood how to do this to produce mirrors to the skyscraper sheaves of points. Basically, one way to produce mirrors to points is to consider circles that live completely inside the components and take thimbles on these. So like this object L sub p on this picture. It's known that the thimbles on these Lagrangians, suitably equipped with extra data, produce mirror to skyscraper sheaves of points on the non-Archimedean curve whose valuation is not that. I mean, basically, you need to exclude the points whose valuation lands inside the triple point, so inside the pair of pants. But most points can be obtained here. So now a line bundle is something whose X with a skyscraper sheaf of points is always of rank 1 everywhere. And so that tells you that line bundles should come from trivalent graphs on these configurations of curves. So something like this L0 that I've drawn. And so in the case of the pair of pants, what you would like to be able to understand is if you take the union of this trivalent configuration consisting of R plus inside each coordinate axis C, inside C cubed, and you define some version of wrapped Floer homology inside this union of the coordinate axes, why does this reproduce the ring of functions of a pair of pants? And of course, what does this mean is maybe a more immediate question. Okay, so here's a bit of motivation or explanation for what is going to happen. So in my other project with Abu Zaid, we produce mirrors to line bundles by parallel transport of R plus squares inside C star squared along U-shaped curves in the base that stay away from the singular fiber. Remember that the discussion here did not, I mean, we had some holomorphic curves passing through there, but the Lagrangians themselves stayed carefully away from the critical locus. And things don't look like thimbles at all. I mean, they're fibered over arcs, but there's 2 ends at infinity, not 1. So one observation, though, is that even though we don't have a thimble in the sense that I explained before, we can produce, there's a glimmer of hope when you realize that you can produce a piecewise linear Lagrangian that behaves like a thimble, except you don't know how to smooth it, and therefore you don't know how to make it into an object of a Fukaya category. This would be basically by observing that if you just take this model of C cubed project into C by the product of coordinates, then the vanishing cycle associated to the origin is in fact a Lagrangian torus T2 inside each C star squared fiber. And if you parallel transport arcs coming out of the origin inside the coordinate axis, then you'll get Lagrangian cylinders with boundary on that torus. So if you just naively parallel transport a trivalent graph, you will get a piecewise linear thing consisting of a torus with 3 cylinders attached to it. And the observation is this is something which, if you use the log map to project C star squared to R squared, this is something that lives completely over a trivalent, this kind of tropical curve, basically. So the other remarkable thing is that this vanishing cycle actually does smooth to something called the tropical Lagrangian pair of pants, which is something that has been studied a couple of years ago by various people. There's constructions by Diego Matesi, by Grisha Mihalkin, by my student Jeff Higgs, probably some others. And indeed, if you look at the U-shaped Lagrangian, even though its ends normally were just two different R plus squares inside C star squared, those were connected by a mapping cone, and one construction of a tropical Lagrangian pair of points, in fact in Higgs, is exactly as such a mapping cone. So there is in fact a vanishing cycle, this tropical Lagrangian pair of points associated to this trivalent graph, even though we do not know how to build a thimble object. So the key point now is that if you want to calculate the Homs in a Fukaya category of a thimble with itself, normally what you do is you perturb the thimble so that intersections lie at the origin, and then you do a calculation at the origin. And that's what we will pretend that we are doing in the rest of the talk. But the way you would do it here to avoid the issue that we don't really see what exists at the origin is instead to perturb differently so that there are two sets of intersections over the origin in the critical locus and in a smooth fiber among the vanishing cycles. Then the intersections between the vanishing cycle and itself, in fact, are twice what you need. It's kind of twice the size of what you want, and 1/2 of that cancels in pairs with intersections in the critical locus using basically parts of a Floer differential that count holomorphic sections over here. So all that to say that a workaround to the inability to understand what happens here could be to look at the smoothed vanishing cycle, compute its wrapped Floer cohomology inside this C star squared, and take 1/2 of it, the correct half. In this case, the degree 0 part. And so what we will pretend is that we can actually compute this directly on the critical locus. So you should imagine that the formulas and definitions that come up next, they make sense in their own right, but their motivation is as a shadow of this geometry of a Landau-Ginzburg model that ends up reformulating things in a way that does not involve an ambient space anymore. All right. Okay, so let's move on unless there are questions. I just realized I forgot to open the chat window or anything, so I have no way of knowing if anybody has any questions. Questions, anyone, before we move on? No? Okay, so let's try to keep going a bit. All right, so now we're going to try to restart fresh and forget about Landau-Ginzburg models and just try to define a way to do Lagrangian Floer theory on these kinds of pictures. So we're going to want to think of the wrapped Floer homology of, say, this graph L0, which is the union of the real positive axes inside the union of free copies of a complex plane. So when we do wrapped Floer homology, we need to perturb Lagrangians in the positive direction at infinity. And this creates a bunch of intersections. And these intersections, the red dots all along here, will give three infinite series of generators in the cylindrical ends. Plus, we will declare that there's one other generator at the vertex. And these will all live in degree 0. And the claim is that these generators should give an additive basis of a ring of functions on the pair of points, since we expect that L0 is mirrored to the structure sheaf of a pair of points. So how do we get a sense of what this basis should be? Well, we can use evaluation at points, remembering that if I take, sorry, yes? No. Was there a question? Okay, not sure. Okay, let me continue. Please interrupt more forcefully if you do have a question. Okay, so evaluation at points. So the point is we know roughly what we know what mirrors of points look like. We don't necessarily know exactly which point is mirror to which Lagrangian, but we know that they should correspond to S1s in the legs together with local systems. That should correspond to skyscrapers of points on the pair of pants near a puncture. And in fact, if I have this circle L sub P, it bounds a disk with some amount of area. The area of this disk for the symplectic form should be equal to the valuation of a local coordinate near the puncture of a pair of pants at the point being considered. Beyond that, further details are kind of less clear because there's in fact no canonical local model. Sorry, I'm not sure why this is doing that. Well, let's not worry. So there's no canonical local model, local coordinates on the ends of a pair of pants near a puncture. One needs to choose one. And similarly, the manner in which a thimble on one of these S1s, so it's going to be a Lagrangian S1 times R2, this is sometimes called the Agenagich-Waffa branes in C cubed. And the way in which this determine objects depends on the choice of bounding cochain, basically an algebraic procedure for canceling the obstruction in Floer theory coming from the presence of this blue disk and of its multiple covers. This is not a Lagrangian that you can, in Floer theory on C cubed, this Lagrangian does not have a well-defined Floer theory, Floer homology with itself until you cancel algebraically by a bounding cochain these holomorphic disks. And so there's not really a preferred choice of local coordinates. We'll have to kind of make a choice as part of our data. Okay, so having talked about points, now if I have a function corresponding to a wrapped Floer generator from L0 to itself, I can evaluate a function at a point by calculating the Floer products from L0 to L0, let's call that f for a function, to L sub p, the generator, the intersection between L0 and L sub p is what I would call the evaluation map at the point P. And so I want to know what is the module structure, if you want, on the Floer complex of L0 with LP. This is going to be a one-dimensional module over endomorphisms of L0. They want to know which point does it correspond to. So I cannot tell you exactly which point because that depends on other data, but what I can tell by looking at the behavior of this like orange triangle that contributes to the Floer product and its behavior as I move the point inside the leg is that the number of times that things wrap has to do with the order of pole of the function f at the given puncture of a pair of pants. So the first return Floer generator here has to be corresponding to a function that has a pole of order 1 at this puncture of a pair of pants. This one will be something that has a pole of order 2 and so on. And in fact, the simplest thing to assume, by analogy with wrapped Floer theory in smooth punctured Riemann surfaces, is that these generators in the ends are successive powers of the inverse of a single local coordinate. So a nice fact is that indeed the constant function 1 and powers of inverses of local coordinates at the punctures of a pair of pants define an additive basis of a ring of functions. It just follows from partial fractions. If you look at meromorphic functions on P1 with poles at the three given punctures, and you do partial fraction expansion. Okay. So a small disclaimer is, in the previous slide, I was explaining how to think of this as imitating Floer theory for the tropical Lagrangian pants in C star squared. I do not know what additive basis of functions one gets out of that. I haven't been able to finish the calculation. So the bases that we will be using, that we will assign to these intersection points in our main construction, might differ from that one by corrections. And these corrections would preserve valuation and vanishing order and so on, but it might not be the same exact functions. It doesn't matter because we can prove homological mirror symmetry anyway. All right. So now comes the more annoying part of the story, which is that we talked about how to evaluate this function f at a point which is in the same, near the same puncture of a pair of pants as where that function takes a pole. So it's in the region where that function has a large, takes large values, has small valuation. But in fact, well, an analytic function is going to be vanishing only at isolated points on a curve. And so it should not, it remains non-zero at the points which correspond to the other legs of the pants. And that tells me that this Floer generator f here needs to have a way to have holomorphic triangles contributing to this mu2 if I place my skyscraper sheaf of points in a different leg of the trivalent configuration. And that means, therefore, that there must exist a holomorphic curve that starts like this and continues and goes into the puncture and then somehow goes out to somewhere over here. And so this forces Floer trajectories to propagate through the vertices of the trivalent configurations. What does the propagation mean? Well, it's something we will postulate when we define Floer theory for trivalent configurations. But it's a shadow of propagation phenomena that must happen also when we think of a Floer theory of tropical pairs of pants. Just because, well, we know, again, that the analytic functions defined by these generators cannot vanish identically on the formal neighborhoods of the other punctures. Okay, so now that the ingredients are in place, here's basically the tentative definition of a Fukaya category. So the data that we will use for a union, for a trivalent union of Riemann surfaces, let's say just the components are P1s and A1s. So there needs to be a symplectic form. So the main parameter is just the area of each P1 component, which will be a positive real number. But in fact, I may want to equip this also with a B field or a bulk deformation, which means that the weight of each P1 will not just be a pure power of a Novikov variable, but just any element of a field whose evaluation is equal to this area AI. And then I will choose what I call chart data at each vertex, which is basically the choice of meromorphic functions on P1, on the pair of pants, basically, functions on the pair of pants, whose extension to P1 are meromorphic with a single pole at the respective puncture. So these are candidates for what the first wrapped return generator of a Floer complex stands for near each trivalent point. And there's a lot of possible choices. The preferred choices for these PIs would be that besides, if I have a meromorphic function with a single pole, what I need to know to determine it up to scaling is where does it have its zero. And it seems aesthetically pleasing to have it take its zero at another point, at one of the other punctures. And so these expressions that you get for such functions, there's two choices for each local coordinate, but observe that they are basically expressions that are defined in a completely, independently of the field of definition. So there's something nice about the lack of any coefficients. Everything would be defined over the integers. Sasha and I have a small disagreement about minus signs. I'm sticking to my minus signs. I know Sasha must be kind of upset at me right now, but anyway. So what is an interpretation of what's the mirror of this sort of thing? So what we're saying is near a maximal degeneration, a curve can be viewed as a smoothing of a union of P1s attached together by nodal points, with each P1 carrying 3 nodes. So what I can do is take P1s with 3 marked points. This will be just becoming my pairs of pants. And I pick local coordinates, and I will set, so I pick local coordinates which are now chosen according to this chart data that I picked. For the, each P1 here will correspond to a vertex. Each vertex corresponds to a P1 here. Each vertex has 3 chart data, which are local coordinates around the 3 nodes attached to it. And then I will have a smoothing parameter, and I can define a local smoothing by replacing locally y prime I equals 0, the nodal curve, by instead y prime I equals t to the area, or in general the weight, the Kähler parameter associated to, so these points, these nodes correspond to the P1s. And there's maybe another way to think about it that kind of helps a little bit. Anyway, maybe I shouldn't try to make a fool of myself by trying to use differential geometric ideas to explain what, the right way to do this is really to build either a formal scheme or a non-Archimedean rigid analytic space out of the data. And so in the rigid analytic sense, what you do is you kind of take your rigid analytic pairs of pants and you truncate them at sizes that are smaller than the areas of the P1s on the symplectic side, and then you attach them together using these kinds of identities. If you're trying to build the whole algebraic space directly instead, then Sasha has a beautiful way of explaining this using a Schottky groupoid obtained by iterating these kinds of coordinate transformations that you glue things between. And you can delete all the limit points and then build directly a scheme out of this. All right. So anyway, let's return to the, oh, sorry. Yes, so let's continue. We have the space. Now let's talk about the objects of a category. So the objects, okay, there's going to be point-like objects, which will be embedded circles inside the P1s. So those we don't really need to say too much more about. And then the objects of line bundle type will be trivalent graphs with one arc on each component of sigma. So we need to pass through all the triple points and to have one leg in each component of the configuration. And we will impose on them that they have a fixed, these arcs have a fixed tangent direction at the vertices. This is like for bookkeeping to make accounting easier. And moreover, there's extra data. So we want to equip these trivalent graphs with local systems of rank 1 over the Novikov field, trivialized at the vertices. So what is the interpretation of that? Well, we want to think of a line bundle on the mirror curve as built by gluing together pieces, which are, okay, so near each triple point, my trivalent graph just looks like this standard configuration, which I've tried to argue should be the structure sheaf of the pair of pants. And in the P1 pieces, we are going to have each time some leg connecting the 2 nodes on that component. The most obvious discrete invariant here is the number of turns that this thing makes inside the P1. And that corresponds to the degree of a line bundle on a P1. And now the fact that we have a local system and fixed trivializations at the ends tells us how to actually have this line bundle with fixed trivializations at 0 and infinity. And now by gluing O's and O of K's with fixed trivializations and choices of isomorphisms at the nodal points, and then smoothing the maximally nodal mirror curve to the space that we want, we are describing a line bundle on it. I mean, you can define explicitly this line bundle by transition functions in the local coordinates, but I'd rather not do that here in the talk. So to define morphisms between objects of a Fukaya category, now we will use a small Hamiltonian perturbation to push the legs at the vertices a little bit, slightly counterclockwise. And if there are some non-compact components, some A1s, that have not been stopped, then we would wrap at infinity in those symmetrical ends. We can also consider versions with stops, or if you want, partially wrapped. So for example, here's a couple of examples of graphs on two different things. This one is the mirror to a once punctured elliptic curve. This one is mirror to a closed genus 2 curve. So I have this red, sorry, the blue Lagrangian L0, and the red one is a perturbed copy where I've moved things slightly counterclockwise near the vertices. And in the first example, I've wrapped at infinity. So now I look at intersections in the usual way as I would for holomorphic curves, for Floer theory on a Riemann surface. And so I get Floer generators of degree 0 everywhere in this wrapped end. By convention, there's one generator of degree 0 at each vertex. And I get in these compact components, just combinatorially, I get that there must be also a degree 1 generator inside. So at this point, these are like mirrors to O on both of the corresponding curves. And at this point, you can ask, well, is this going to work? Does this have any chance of working? One of the first things you can see here, there's 2 degree 0 generators and 3 degree 1 generators. In general, if I take the endomorphisms of a line bundle on a mirror of a closed genus G curve, I'll get 2G minus 2 generators of degree 0 from the triple points, 3G minus 3 generators of degree 1 inside the legs like this. The Riemann-Roch formula holds. This has Euler characteristic 1 minus G as expected. That's a good first indication. Okay, so now the differential and the products on these Floer groups will be defined by counting zero-dimensional moduli spaces of configurations of holomorphic disks with boundary on the given Lagrangians. And the main difference is that instead of just looking at a single holomorphic disk for each Floer operation, we'll now look at chains or trees of holomorphic disks attached together at the vertices. So this is like this propagation phenomenon that a holomorphic curve can start on one component of sigma and pass through a triple point to continue into the next component. So on the picture here, I have an example of 2 intersection points X and Y between 2 Lagrangians A and B on different components. And this can contribute to the coefficient of the output point Y in the differential of X with propagation through the vertex. So how do we decide how to count these things and what is allowed or not allowed at the vertex? Well, there's a rule. Okay, so in general, as usual in Floer theory, there will be weights by symplectic area and holonomy. But now we have these multiplicities for propagation, which are new. So the multiplicities are determined by the chart data. When I propagate through a vertex, there is going to be some input degree and some output degree. Basically, my holomorphic disk, because the tangent directions to all my Lagrangians are very close to a fixed reference direction, I can say this disk at its input covers the input leg with degree 1, and it has degree 0 on the output leg. If you want, degree is basically the rotation number of, so relative homology class or whatever you want to call it. So there's an input degree, in this case 1, an output degree, in this case 0. The input degree is at least 1 because of how the disks are, how things have been perturbed slightly counterclockwise. The output degree could be 0 because of, again, this thing. And now the local multiplicity contribution will be obtained by taking P1 to the D1, where P1 is the inverse of the local coordinate at one of the punctures. So this is a meromorphic function with a pole of order D1 at one puncture of my pair of pants. And now I can expand it in terms of a local coordinate at the other puncture. So this will give me an expansion as a power series in negative powers of P2, since P2 is, again, the inverse of a local coordinate. And then I want to take the coefficient of P2 to the minus D2 in that expansion. All right. So, okay, so this is like the combinatorial rule, and the overall multiplicity will be obtained by taking a product over all propagations. So in the above example, let's say that my coordinates were locally -1 over z plus 1 and 1 over z. I would take P1 to the 1, that's the input power, -1 over z plus 1. I would expand it in powers of the inverse of 1 over z, which is just a fancy way of saying z. And the constant coefficient -1 tells me the weight here. In bigger examples, you would usually get binomial coefficients. In any case, they're always integers if you use the preferred chart data that I listed above. Okay, so you can do fancier examples. For example, you can look at the endomorphisms of L0, which is mirror to the structure sheaf, on this configuration, which is mirror to a once nodal elliptic curve. And so there's a small mystery, which is that there is one degree 1 generator in the Floer complex when everybody else, the x's, have degree 0. And, you know, if you look at the cohomology of O on this punctured elliptic curve, there's no H1. So Y needs to vanish. And you could ask, well, the situation looks completely symmetric between the legs of the, between the upper and lower part of this picture. How will I break the symmetry to have a non-zero differential from x0 to y? So from x0 to y, actually, there's no breaking of symmetry. There's one holomorphic disk here, one here. So the differential of x0 is 0. And this is consistent with the idea that x0 corresponds to the constant function 1, in fact, on our punctured elliptic curve. But now, if I look at the next one, x1, the first generator, is going to have trajectory coming out here that can propagate. It could propagate either down here or up here, and with various degrees. To know what's the contribution, well, you see that you expand basically this local coordinate attached to this leg in terms of the other local coordinates. And for the choices I've made, you get a 1 on one side, a 0 on the other side. This will tell us that really x1 is not a closed thing. The two possible paths propagating downward or upward do not cancel out. And same for the others. So what this gives is that, well, because of this, the generator, there's no H1 left, and H0 behaves as we expect. Remember, on this punctured elliptic curve, there is no regular function with pole order 1. There's the constant function 1, and then the next thing has pole order 2. And then there's one extra function for each successive pole order. And in fact, you can get the ring structure to match as well. Okay, so since my time is almost up, this is time to actually get to the statement of the theorem, which is that basically the Fukaya categories defined as above are derived equivalent to coherent sheaves on the mirror curve obtained by the gluing of P1s relative to 3 points in the way explained. So the proof of that relies on a perturbed model for calculating Floer homology on the trivalent configurations that's very similar to what was in the thesis of my student Heather Lee for calculating on smooth punctured Riemann surfaces by chopping things into pairs of pants. So now instead of cutting things into pairs of pants, now instead we chop our trivalent configurations into mirrors of pairs of pants. And we can use basically something very similar to Heather Lee's technology, which is do a sharp Hamiltonian perturbation inside each cylindrical part. So here inside each P1 component to introduce infinite dimensional extra canceling pieces of the Floer complexes. The point is, okay, so first of all, there's like some wizardry with the homological perturbation lemma to show that this modification, despite the need to take completions, doesn't change the Fukaya category. The next observation is that after you do these perturbations, the intersections and the Floer trajectory is kind of localized to pieces that are mirrored to the single chunks. There's a non-crossing lemma due to Heatherly that kind of applies here, basically. Maybe here it's more a tautology, I don't know exactly. That says that intersections outside of these neighborhoods P sub V of the vertices, including the central origin, form, sorry, the intersections that are not in there span A infinity ideals. So that means if any operation in Floer theory has an input that's not in P sub V, then its output is also, then its output is also not in P sub V. So that tells me that in fact, these categories after perturbations can be calculated as limits of restriction diagrams. And this matches exactly how you would calculate dB of a mirror curve from a restriction diagram for, well, I guess if you take the non-Archimedean viewpoint, an aphenoid cover of the mirror curve. Okay, so I think this is, sorry, I'm over time, so this is a good place to stop. Thank you for your attention, and I hope that was somewhat understandable.
Questions, comments? Well, if everything is clear, then let's thank Denis again.
And let's thank Sasha for giving us the opportunity to celebrate things also, and the organizers for making this happen. And I hope that there will be, I don't know what the restrictions are in Moscow, but at least I hope that people can celebrate responsibly. And I saw recently actually this video of how somebody from the consul of Sweden, that basically the consulates of Sweden have been giving chocolate Nobel medals to various Nobel laureates in their country of residence because of a lockdown. So they're having like small outdoor ceremonies where they receive a fake Nobel Prize from their local Swedish ambassador. But anyway, I hope that Sasha does get an EMS prize in some physical form and not just like that.
Don't steal it.